Welcome to G Fun Facts Online. Today, we are traveling to a place where the concept of water feels like a distant memory. Imagine standing in the center of Death Valley. The sun beats down on the cracked earth, and the air itself feels thirsty. It is one of the driest places on the planet, a landscape of salt flats and searing heat, where survival feels like a defiance of nature. Yet, in this crucible of aridity, a black, window-sized panel stands silent and still. It has no plugs, it has no moving fans, it has no loud compressors. It simply sits there, breathing. As the sun climbs higher in the sky, something miraculous happens. Droplets of pure, crystal-clear water begin to bead on the glass, trickling down into a collection tube. By the end of the day, this passive device has wrung a cup of life-sustaining liquid from air so dry it cracks human lips. This is not magic. It is the cutting edge of material science. It is the marriage of ancient geometry and modern chemistry, a technology where origami meets hydrogels to quench the world's thirst. In a world where fresh water is becoming the new gold, the race to unlock the vast atmospheric reservoir is heating up. We often forget that there is a massive ocean floating directly above our heads. The Earth's atmosphere is a colossal, invisible river. At any given moment, the sky holds approximately 13 trillion liters of water as vapor. It is a renewable resource constantly replenished by evaporation from the oceans. For decades, we have looked to the ground for water, draining aquifers and diverting rivers, but now, scientists are looking up. The solution they are finding lies in a squishy, jelly-like material folded into complex shapes, capable of pulling drinking water from the driest deserts on Earth. To understand the magnitude of this breakthrough, we must first look at the history of harvesting water from the sky. For centuries, civilizations have tried to tap into this resource. The Incas collected dew, and even today, the people of the Atacama Desert use fog catchers. These are massive mesh nets that snag passing clouds, dripping water into buckets below. But these ancient methods have a fatal flaw. They require high humidity. Fog catchers need thick, moist banks of fog to work. They are useless in the true deserts, the arid interiors where billions of people live on the razor's edge of water scarcity. Modern engineering gave us a solution in the form of atmospheric water generators, or AWGs. These are essentially heavy-duty dehumidifiers. They work by cooling air until the water condenses, much like a cold soda can sweats on a hot day. While effective, these machines are energy gluttons. They require massive amounts of electricity to run compressors and fans. In off-grid villages or disaster zones, places where power is as scarce as water, these machines are essentially glorified paperweights. The holy grail of water science has always been a passive system, a device that needs no electricity, works in bone-dry air, and runs on the only abundant energy source in the desert, which is sunlight. This brings us to the star of our show today, the hydrogel. The heart of this new technology is a material that, to the naked eye, looks like a cross between a contact lens and a piece of jello. At a molecular level, a hydrogel is a tangled network of polymer chains, long, spaghetti-like molecules that love water. Hydrogels are not strictly new. They are the magic ingredient in disposable diapers that allows them to soak up massive amounts of liquid. But there is a catch. A standard diaper can only hold liquid water. It cannot grab water vapor out of the air. To turn a hydrogel into an atmospheric sponge, researchers at MIT, led by Professor Xuanhe Zhao, had to supercharge it. They infused the hydrogel with lithium chloride, a specific type of salt. If you have ever seen a salt shaker clog up in humid weather, you know that salt is hygroscopic. It naturally attracts moisture from the air. Lithium chloride is the absolute champion of this property. It is so thirsty it will pull water vapor out of the air with as little as 20% humidity, which is typical of a desert afternoon. However, the chemistry wasn't simple. Simply mixing salt into a gel isn't enough. In early experiments, the salt would dissolve in the water it captured and leak out, rendering the device useless after a few cycles. The breakthrough came when the researchers added a third ingredient called glycerol. This common compound acted as a stabilizer, locking the salt ions into the polymer network so they could capture water without being washed away. The result was a supermaterial, a hydrogel that could sit in dry air and aggressively suck in water vapor, swelling and becoming heavy with moisture. But capturing the water is only half the battle. You have to get it back out so you can drink it. This is where the ancient art of paper folding, or origami, enters the equation. In the world of surface chemistry, shape is everything. A flat sheet of hydrogel is inefficient. It has a limited surface area exposed to the air, meaning it takes a long time to absorb moisture and even longer to release it. In a passive system driven by the sun, speed is crucial. You only have a few hours of peak sunlight to heat the gel and release the water. The MIT team realized that to make the system viable, they needed to maximize the surface area without making the device massive. They turned to nature's favorite geometric trick, which is folding. They molded the hydrogel into a 3D structure that resembles a black, architectural bubble wrap. This isn't just random texture. It is a calculated origami array of microdomes. Why does this bubble shape matter? First, it improves absorption. The dome shape exposes more surface area to the air, allowing the thirsty salt ions to grab moisture from multiple angles simultaneously. Second, it improves desorption, or the release of water. When the sun hits the black hydrogel, the heat needs to penetrate evenly. The thin, curved walls of the domes heat up much faster than a thick, flat slab would. Finally, it creates a breathing motion. As the hydrogel swells with water, the origami domes physically expand. When they dry out, they shrink. This literal swelling and shrinking helps cycle the air around the material, keeping the process dynamic. The device operates on a simple, rhythmic cycle, perfectly synced with the desert day. Think of it as a mechanical lung. During the night cycle, the box is open to the air, the desert cools, and the relative humidity rises slightly. The hydrogel bubbles greedily absorb water vapor, swelling up and storing the moisture inside their polymer chains. The salt locks the water in, preventing it from evaporating back out. Then comes the day cycle. When the sun rises, the box is closed. The black hydrogel acts as a solar absorber, heating up rapidly. The heat breaks the weak bonds holding the water molecules to the salt. The water turns into steam, rises, and hits the cooler glass cover of the box. There, it condenses into liquid droplets and flows down into a sterile collection tank. Theory is one thing, but the desert is another. To prove their device worked, the researchers didn't go to a humid backyard in Boston. They went to Death Valley. In the blistering heat of the Mojave, where relative humidity often drops below 20%, most passive water harvesters fail. They simply cannot pull enough moisture from the parched air to overcome the rate of evaporation. But the Origami hydrogel device was set up on the valley floor, and the results were startling. Even in these punishing conditions, the device produced drinking water. The bubble wrap design proved to be a game changer. The accelerated kinetics allowed the gel to release its captured water quickly during the limited window of peak sunlight. The test showed that a single square meter of this material could generate several liters of water per day in moderate humidity, and a survival-sustaining amount even in extreme aridity. For a hiker lost in the dunes, or a soldier at a remote outpost, a device the size of a backpack could mean the difference between life and death. Now, while MIT's hydrogels are grabbing headlines, they are not the only players in the water from air game. Just across the country at UC Berkeley, another scientific titan, Professor Omar Yaghi, has been pioneering a rival technology known as metal organic frameworks, or MOFs. If hydrogels are like super sponges, MOFs are like molecular cages. They are crystalline powders made of metal atoms, connected by organic linkers, forming a 3D lattice with incredibly vast internal surface areas. A single gram of MOF powder, if unfolded, would cover a football field. The pores in these MOFs are engineered to be the exact size of a water molecule. This means they can be incredibly selective. They don't just absorb water, they trap it in a lock-and-key mechanism. There is a fascinating clash of technologies happening here. MOFs operate brilliantly at ultra-low humidity, even down to 10%. They are precise and efficient, but historically expensive to manufacture, requiring exotic metals like zirconium. On the other hand, hydrogels are generally cheaper to produce, using common polymers and salts, and they can carry more water by weight. The introduction of the origami structure has helped hydrogels catch up to MOFs in terms of speed and efficiency. The competition between these two technologies is driving rapid innovation. We are seeing a divergence in application. MOFs might be used for high-end, medical-grade water generation in the driest of dry environments, while origami hydrogels could become the people's solution, a low-cost, mass-producible sheet that can be rolled out on rooftops across the developing world. The implications of this technology extend far beyond cool science experiments. We are facing a global water crisis. According to the World Health Organization, by 2025, half of the world's population will be living in water-stressed areas. In places like sub-Saharan Africa, rural India, or the arid coasts of Chile, infrastructure is the enemy. Building pipes, pumps, and desalination plants costs billions and takes decades. A passive water harvester bypasses infrastructure entirely. It is decentralized water. Imagine a future where every home in a drought-stricken village has a panel on its roof, right next to a solar panel. The solar panel provides electricity, and the hydrogel panel provides water. No pipes, no monthly bills, no reliance on a failing municipal grid. This also has massive potential for humanitarian aid. In the wake of earthquakes or hurricanes, water lines are often the first to break. Cholera and dysentery follow soon after. Airdroppable crates containing these lightweight, passive harvesters could provide immediate, sterile water sources to refugees and disaster victims without the need for diesel generators or fuel convoys. The technology is even being adapted for agriculture in the form of self-watering soil. Scientists are experimenting with mixing the hydrogel directly into the earth, At night, the soil itself would absorb moisture from the air. During the day, as the soil heats up, the water would be released directly to the roots of the plants. This could allow farming in regions where rain is a memory. Of course, the Origami hydrogel is a triumph of human ingenuity, but it is not yet a household product. Challenges remain. Scalability is the first hurdle. Making a window-sized prototype is different from manufacturing millions of square meters of specialized polymer. The cost needs to drop from hundreds of dollars per unit to mere pennies to be truly accessible. Durability is another factor. The desert is harsh. Sandstorms, UV radiation, and extreme temperature swings degrade materials. The hydrogel needs to last for years without losing its sponge-like ability. And finally, there is output. While a few liters a day is enough for survival, it isn't enough for a shower or a washing machine. To replace the tap, these systems need to become more efficient, or homes will need massive arrays of panels. However, the trajectory is clear. The efficiency of these devices has doubled and tripled in just the last 5 years. Startups are spinning out of university labs, and venture capital is flowing into the sector. For most of human history, looking at the sky for water meant praying for rain. We were passive recipients of nature's whims. When the clouds didn't come, civilizations collapsed. The Origami hydrogel represents a shift in our relationship with the planet. It turns the atmosphere into a reliable utility. It proves that with the right geometry and the right chemistry, we can wring sustenance from the most unforgiving environments. As we stand on the precipice of a hotter, drier future, these black, bubble-wrapped panels offer a shimmering hope. They remind us that even in the driest Death Valley, the air is alive with the promise of water, if only we know how to fold the catch. Thank you for listening to G Fun Facts Online.